right, so welcome everybody to the second workshop series as part of this quantitative methods for HIV researchers. This one's going to be a little bit more statistics and data science, statistics focused, and some new stuff on predictive modeling. So it's going to kind of follow a lot of the same course as kind of what we did in the last 6 classes, where we're going to be going on to DCC on demand and, kind of following along with some kind of pre-rendered R markdowns and whatnot. So first off, does everyone have access to DCC on demand, working that, and the GitLab? Okay, so we're gonna first off set up our studio app. So if you want to follow along here, when you go into the CHSI RStudio workshop, what you're going to want to do is, instead of clicking for the singularity image, you're going to want to click testing as opposed to the R25. We'll get this fixed at a maybe potentially later one, but just use testing for now. And click launch. And we'll wait for it. And then connect. And then you should potentially have access to this 2023-2024 HIV workshop. And if you haven't checked it since the last one, you're just going to want to do a pull down to make sure you get everything up to date. So I want to pause here just to make sure if anybody has any problems so far with this aspect. If not, we can kind of get into some of what we're going to be working on in this seminar. Yeah. So yeah. Oh, okay. So yeah, you log on to DCC.
Yeah, I'm already on DCC.
Okay. Yeah, and so you weren't in. Were you in last one? Okay. All right. So we're gonna just figure out the. I'll put the GitLab. Try to get the link up here. And so what you're going to want to do. Is environment. Okay, here we go. Okay. So you're going to want to basically go to this website, HIV-R25, and then once you're there, okay, you're there. Does it pull up? Yeah, no problem. Does it pull up? Okay. Yeah, I think it's yeah. Yep. Okay. And then it should pull up this basically. And then you're going to want to do a clone. So basically you're going to copy this URL. And then you're going to go to here and you're going to say like new project. And say version control. Git. And then you're going to just copy and paste there and it should just download everything. Yeah, let me know. Everybody else, you nailed it? Yeah. And then just copy that URL down. How are other people able to pull it down? They got the most recent version. Yes. On Zoom, thumbs up, reaction, or not. Oh, we got one. All right. They're going through.
Sorry,
No, it's okay.
let me do it again.
Oh no, so go back up. No, not that. Go back to the other get page. The tab. So good. Oh yeah, that's the other one, which you just had.
Oh, the,
Okay, so code, and then copy that one. Now. Yeah. Great project. All right. Should be good. Okay. All right. So, we're going to be basically, so you want to navigate down here to the workshop_2 statistics. And then we basically have, as of now, there's only about 2 R markdowns in there. The day 0 one, you can ignore. That's just kind of some data cleaning of one of the example data sets that we're going to be using. Feel free to look at that if you'd like, but we're not going to be covering it today. And so we're going to be talking about this day 1.R markdown, and then I'll also open up the compiled version, which has it's all prettied up. So there's a sign-up sheet. I'm just getting this out of the way now instead of at the end. So feel free to click on that and just put an X by your name, or if you're not on there, just add your name and put an X on today's date. This just really helps us with kind of measuring the success of the course and whatnot. Okay. All right. So, introduction. So basically, today we're going to go over a couple different. Oh yeah. What's up? No, it's okay. I thought I changed it. I thought I was doing so well. Let's see. That's view only. All right. You know what? I'm going to do this when we have an exercise later instead of right now. So, all right. So today we're going to be talking about kind of a few different key elements. So we're going to be discussing kind of some details about the scientific process and why statistical analysis is so important. Okay, and then we're going to be talking about populations versus samples, some common study designs you may run into. We're going to be talking about numerical summaries such as data types, common data types, some measures of central tendency, your mean and your median, and then measures of spread, your like standard deviation or IQR. And then we're going to go over some graphical summaries such as bar plots, histograms, box plots, and scatter plots. And to kind of frame this, we have 2 different case studies that we're going to be working on. The first one is this efficacy trial of this DNA RAD5 HIV-1 preventative vaccine, where we have a link here to the publication. And the data is publicly available through SHARP, which is a HIV research group out of Fred Hutchinson Cancer Research Center in Seattle. We've downloaded the data so far that we're going to be using. It'll likely be updated for maybe the later half of this workshop series. And so this is a kind of a pretty rich data set. It was a trial of this HIV vaccine in 2,500 men or transgender women who have sex with men, and basically measuring the efficacy of this vaccine. It wasn't effective, which is why you probably haven't, maybe you haven't, why we don't have a vaccine. So we'll be talking about that data set a little bit. Then later on in the second half, we'll be talking about a subset of that data set, which has really rich immune features. And so that's going to be case study 1. So it's pretty rich. So we have information on publication ID, their treatment, whether or not they're HIV negative at day of first injection, this information of they were infected, follow-up time, and more stuff. Whether or not they were per protocol, they received all 5 vaccine shots, and so on and so on. And age, gender identity, categorical race, BMI categorical, this baseline behavioral risk score, and then in some cases, cause of death. So it's a lot of data. It's about 2,500, and then so kind of looks like this: placebo, publication ID, treatment, and then the information about adherence, and then so on and so on. Age, self-identified race, BMI category, this risk score, and we're going to get into more of this stuff later on in the workshop. Yeah, I'm hoping to, I see in the chat, I'm hoping to correct that, the Zoom, the Slack, not the Slack, the sign-up sheet during an exercise later. Okay. And then case study 2 is the superiority of viral load over CD4 cell count when predicting mortality in HIV patients on therapy. It's publication with some data that was in the supplement that we downloaded. Duke has very strict publicly available data sets. So for a data set to be publicly available, you have to be able to download without logging in, basically. So this is some data that we've downloaded that was published in BMC Infectious Diseases in 2019. So these are going to be 2 of the data sets that we're going to be using, but the first data set is probably going to hopefully take up the majority of our focus. Okay. All right, so let's kind of run some code first off to get some of this stuff loaded. So we're going to basically run the libraries that we need. You can kind of ignore some of these messages. And then we'll kind of load the data. So as a refresher from last seminar, this will read the data set in. This is reading the dictionary. And then this part is basically taking the dictionary that we've read in and putting in, just kind of displaying it in a nice form. Well, maybe a nice form. Kind of in this table form. And then this is just showing the first couple rows of that data set. Okay.
I get a no error in my library.
Did you load when you launched it, did you go to the testing or pack? So when you launched the DCC?
I did make that. You initially launched it without switching into the testing.
It should be there because I'm logged in via the testing as well, and I'm getting those R packages working. Could you double check? And then case study 2, read that in. We're going to do a little mutation out of this log10 viral load. And for this, we're just going to use the baseline, the time point 0. So, okay. All right. So any questions so far? Yes, things seem good. We haven't really gone over much, so. show the code here. If not, did that?
I did not fix it. And then I have it.
Okay, let me. How about, so we're not going to actually have much coding for a little bit. So how about, I think I'll come and ask about that after this, during this exercises. All right, cool. Okay, so let's talk about the scientific process real quickly. So it's kind of built up of a variety, 6 different steps. You have, you observe some kind of pattern, you develop a research question, you develop a hypothesis, you design a study, you collect data, there's a statistical analysis, and then a write-up of kind of the results and conclusion. So for case study 1, the observation is basically there's no effective vaccine for HIV. Part of this challenge is the differing clades of HIV. There's different types of HIV virus right across the world and different geographical locations. So does a multi-gene, multi-clade DNA prime recombinant adenovirus type 5 vector boost vaccine provide any vaccine efficacy? All right. And so for case study 2, adherence to antiviral medications is vital. Is there a difference in HIV control between those who adhere to their medications versus those that do not? All right, so these may be, kind of something you observe, and then from there you kind of want to build up a research question. So on that, for case study 1, it's basically looking at, all right, if we use this vaccine, will it provide any potential efficacy in comparison to just say placebo, what have you? And then for case study 2, it's, is there a difference in HIV control based on whether or not people adhere to their medications or not? Okay. So next up, kind of the primary outcome and hypothesis. So in the simplest kind of form, the research hypothesis is a statement about, what the results are thought to be, kind of desired answer to the research question, and it needs to be stated in a way that is testable and measurable. So specifically, the research hypothesis must be stated in terms of some primary outcome, which is some characteristic that is suitable to answer the question of interest. It needs to be measurable. It needs to be clinically meaningful and of greater importance to whatever the researcher is potentially interested in. And it kind of has 2 components, the null and alternative, which we'll kind of go over later. So in case study 1, we talked about the vaccine efficacy. So one of the things is how can efficacy be measured? These kind of things are usually either defined by the literature or kind of by the science field in general, or it's something that the researcher has to kind of define. So for efficacy, right, it may be how well does the vaccine do in decreasing the risk of a potential outcome, here, infection by HIV. So the research hypothesis then may be, does the novel vaccine, display any efficacy? So the target vaccine will maybe decrease the risk of HIV infection. Okay. For case study 2, we have adherence to antiviral medication is vital. So is there a difference in HIV control between those who adhere or not? So what does HIV control mean? Right? That's something you have to ask and figure out before you start measuring. And you can't test anything, right, if you don't know what HIV control is. So here it typically means undetectable viral load, right? It's pretty commonly defined as less than 50 copies per milliliter over some maybe follow-up period. So the desired hypothesis, the research question is basically there is a difference in HIV control between those who adhere versus not. So there'll be a difference in the occurrence potentially of undetectable viral load over that follow-up time between, say, those who adhere to medication versus those that do not. All right, and then again, we'll get into kind of the statistical hypotheses, which are the null and alternative later on. Any questions so far? No? Okay. All right. So next up, We're going to go over basically study design and data collection. So we're going to be talking about, say, population versus sample, some study descriptives and classifications, and common types of, say, biomedical studies, and what are some sampling techniques that could be used. So the underlying principle, right, of statistical reasoning and inference is, you want to try to describe something about some target population. Overall potential observations, right? So in some examples, all treatment naive individuals living with HIV, all new HIV infections in 2020, all people within 1 hour driving distance, let's say, of Duke North Regional, is that the one that's up on Roxborough? All people, say inpatient clinics of US hospitals with at least 100 beds, all homes within a specific geographic region, right? These are kind of examples of populations. So another example may be height. We'll always do height of people taking workshop series 2, right? That'd be a population because it's very defined to this workshop series 2 in 2024 at Duke. So due to the potential cost, right, or you can't really measure everybody or measure that information, you want to get information on some subset of the data to basically look at that population measure of interest. So, we have this population, and then we take some small collection right here of data that has information, right, and then we evaluate it within that sample. So back to our height question, right? Let's say I wanted to take a sample of height. I could say sample the 4 people that are within the class that took the workshop series 2, right? I can't measure the 5 people that are on Zoom height. So that would be a sample. Just out of curiosity, could anybody see any potential problems with that? Hypothetical problems? Right. So is there a difference? You showed up in person versus Zoom, but it could be right. Well, is there potentially a difference in height between those that come to person versus coming to Zoom? Probably not. That'd be very weird if there. Not. It wouldn't be weird if it'd be. Yeah, that'd be odd. So, all right. So that could be a sample, right? That we could get, a convenient sample. So. Okay, yes. So when we move into that, right, we'll now talk about some study descriptions and kind of classification. So when basically running a study, you have to have the appropriate terminology to kind of describe the study. So there's kind of 2 options in terms of control over the study environment, right? You have experimental, which is basically you control the study, and observational, right, where you're just kind of, it's observing. And then there's the timing of the study, whether it's retrospective or prospective. There's the measurement of the timing/spacing, so whether or not single observation, it's longitudinal observations, or there's some kind of spatial, you're looking at geographic locations and whatnot. And then some additional terminology that's important to know is that blinding, double blind, which comes into play in like case clinical trials, right? Okay. Any questions so far? No? All right. So experimental study is one where you are manipulating the environment in which the participants exist. So this is basically, you're either introducing something new into their life, say like a medicine, diet, training, you're monitoring their device, something, or altering what it currently exists, say changing the environment, increasing the dose of a medication, or something along those lines. And the goal is to study how the effects of that change influence whatever the primary outcome is. So in that case 1, right, we're altering it by giving these people this vaccine, this 5-dose vaccine. So an observational study is a sit back and watch. There's obviously more involved in that than just sitting back and watching. So basically data are collected from some existing environment or database, and collection of those data does not appear with the system in place. So neither the individuals under study nor basically study variables of interest are manipulated in any way, and they're just observed and measured as is. So these are, involve maybe potentially less work. You're not changing things, right? But there's still obviously a lot of work involved. So 2 questions. So case study 1, right? So that was this phase 2B efficacy trial looking at this risk population. There's 21 sites and randomly assigning these people to vaccine or treatment. So what kind of experiment is that? What I just said. All right, it's an experiment, right? All right, and so case study 2, the data used in this study was obtained as secondary data from the University of Vinda in South Africa. The study included a selection of 320 HIV patients on antiretroviral therapy who fulfilled some entry criteria from a longitudinal cohort of 1,092 HIV-infected patients, followed at a wellness clinic in Bela Bela, South Africa from year 2005 to year 2009. So what kind of study is that? It's observational, right? It's almost like we picked these two for having opposing things. Okay, so next up is kind of the timing of the study. So since experiments kind of require manipulation of the control, the condition, and the treatment, these are prospective studies. The terms prospective and retrospective can also be applied within observational studies. So prospective, the study is designed to collect data into the future. Retrospective, the study uses data collected in the past, and the information existed before kind of the study was started. So this can be survey data, EHR data, say baseline data of a clinical trial, and so on. So this is kind of referred to when the data was collected, but not where the data occurred. So was there a television in your childhood home could be determined prospectively or retrospectively. So any questions on the timing of the study or anything so far? We're kind of rolling. Oh, okay. All right. So measurement timing. So this is kind of when are you measuring everything for this kind of sample that you've chosen. So there's a single observation. So this is just information is collected at one point for each sampling unit. So sampling unit here is kind of the main unit of measurement. So in that height example, right, everybody in here is one sampling unit. Longitudinal, the study collects kind of repeated information on the same individuals over time in order to measure some change, either in some variables of time or risk or something along those lines. And then spatial is we're collecting a set of variables across different locations on each sampling unit with an intent to determine if there's some geographical areas that are different from others. So an example may be looking at like air pollution, right, and proximity to certain highways or something along those lines, and measuring the association with, say, lung function outcomes. So in those last two cases of longitudinal and spatial studies, there needs to be some additional care to be taken into account for the fact that you have correlated measures, right? Observations from the same individual measured longitudinally are likely to be very heavily correlated, and observations, right, for that pollution from individuals who maybe live in the same neighborhood are likely to be correlated if using that spatial data. And so this kind of feeds into something we'll be getting into, I think, later, where basically, one of the assumptions of a lot of statistical analyses, right, is independent observations. When that's not met, right, you have to additionally model that correlation in some way. And then finally, we get into kind of blinding, which goes into our clinical trials. So there's 3 different terms. We'll kind of say single blinded. Study participants are unaware of what group they're in. Double-blinded, both the participants and the people interacting with them do not know what treatment that person is getting or what experiment, right? So they don't know whether or not they're injecting that person with the placebo or that, 5 viral booster. And triple-blinded means that not only do those two groups not know what's going on, but also the people analyzing the data do not know group assignments. This obviously blinding may not always be possible, such as surgery, physical therapy, but such experiments are unblinded by default. Any questions so far on study descriptions and classifications? No? Okay. All right. So next up, we'll kind of talk about some common types of biomedical studies. So we'll go over some for observational, then we'll go over some experimental. So some observational studies. So types are cohort studies, case control studies, cross-sectional studies, some experimental study types, clinical trials, pragmatic trials, lab experiments, say randomized designed studies. So these are kind of some very common terms, but it's just for us to kind of understand. So observational studies. First off, we'll talk about cohort studies. So cohort studies is where you have a group of individuals who kind of belong to the same group, and you're kind of belong to the same group, and they'll never belong to, say, a different group, and you're kind of defining that very early on, and then you're just basically kind of following them up for some variables that are of interest over time. So case study 2, they mentioned that this was part of a longitudinal cohort of 1,092 HIV-infected patients that were followed at this wellness clinic. And so that's kind of the overall cohort that they're potentially doing this sub-cohort analysis of. So a very famous example of a cohort study is, say, the Framingham Heart Study, which maybe people have heard of, where they measured these individuals in Framingham, Massachusetts, over, I think now 70 some years, right, over multiple different cohorts and whatnot, different generations. But it wasn't necessarily, they're just following general kind of health status over this group. Case control study. So this is where you're sampling based on some outcome, right? So if you're studying an outcome that is relatively rare, say like colorectal cancer or something like that, you may not have a sufficient sample, right? Just by observing some cohort that would satisfy, say, some power or something like that. So you're specifically sampling and trying to collect people that maybe potentially have this outcome. So in this case, cases are a cohort of people selected from the population who meet some criteria. In that example, colorectal cancer. And this could be related to one or more different risk factors, right, that you're trying to study. And then controls are potentially a cohort of people selected from the population who do not have that criteria, but are as similar to the cases as possible in all groups. So these are often retrospective studies in which people are selected based on these two categories. And then you kind of look at it with regards to some risk factor of interest, or you measure some, say, genomics or antibody data. If there's blood samples, right, maybe you go back and you measure some immunological measure or something along those lines. And then there's additional matching that could be done, right, to make sure that you have the most like cases and controls in terms of age or sex or other comorbidities that may be of interest. Okay. And then finally, we have kind of cross-sectional studies, which are just an observational study in which data are collected on sampling units at only one point in time. So this could be used to just describe the characteristics of a population just at a single point, measure prevalence of a characteristic or disease of interest at a point in time, or kind of look for associations with sampling unit characteristics. So, in our case, case 1 is we just have a single point in time, but analyzing case 2 just at baseline, right, is cross-sectional essentially. Or, cross-sectional would be measuring everybody on the second floor of Hawk that's here right now. I don't know what we're measuring of them, but we're measuring something about them. Okay. Any questions so far? Nope. Okay. All right. Next up, experimental studies. So here we kind of have the clinical trials, which I think a lot of people are likely aware of. So these are prospective experiments involving humans or animals to study safety and efficacy of some new treatment, such as drugs, intervention, diet, what have you. They can be randomized or not. If they're randomized, the participants are assigned to basically different arms, right? Or whether or not they're getting some treatment or placebo, or, you know, with or without certain, say, adjuvants or something with regards to, say, the vaccine that they're getting. And this kind of randomization is to make sure that you're kind of ensuring that the groups are the same, with the exception of some experimental treatment of interest. And then usually there's multiple different parts of kind of a clinical trial and phases to kind of look at, say, measuring the safety of the proposed treatment, and then the efficacy and what have you. So case one, which is the HVTN 505, was a randomized, double-blind, placebo-controlled trial. It was a phase 2B, and I'd have to remind myself of the different phases of the clinical trials that are defined by by everybody. Okay. So pragmatic trials are more kind of related to a real-world setting, so you're not controlling as much. Lab experiments are conducted in labs that do not involve human subjects, so there's a lot more control over environment. So this is, say, mouse models, non-human primate models, and these are usually over a much smaller group of sampling units, and can be completed potentially relatively quickly, so they can be just as expensive. I know non-human primates is a very expensive model to study. And so finally, randomized design study. So this is just some general term for any kind of study that has some randomization. And so there's a variety of study designs that fall into here. And so this is something that you kind of have to think about and discuss prior to collecting data. So this may be, say, across different schools within a county. Maybe you randomize at the school level a different, say, weight loss program. So school A may get one program and school B gets a different program. School C gets no program, right? And you measure something, say, child's BMI or child Z weight or something over after the study. So now we'll go over some of the advantages of the experimental versus observational study. So the advantage of the experimental study is you have a strong design, you have a strong model for showing causality. So causality, right, is kind of often what we're looking for is that A directly causes B, right? And so in these experimental studies where you're controlling for a lot of those potential confounders, you really have you can get some strong evidence for a causal model of whatever you're looking at. This prospective nature gives researchers control over what data they are collecting. And because of that kind of control, you're not maybe suffering from confounding effects that, say, you would in a cohort model. Disadvantages is they're very expensive. They can take a long time to complete. You're going to have dropouts and missing data. And your inference is going to be restricted to those that were included in the study. So they may not necessarily be applicable to the general population. So advantages of observational studies. So you can kind of discover long-term relationships between exposures and outcomes. They can be cheaper and faster if the data already exists, right? You can study potentially rare exposures in cohort studies and rare outcomes in case control studies, right, that you may not be able to do in HIV infection. So for example, in case study 1 of that 2,500, now they stopped the study early, but only 80 individuals got infected with HIV, right, which is relatively small and kind of low powered. So, which is good, it's good, people aren't getting infected with HIV, but because you're not going to be collecting as much as you would in a case control study. Disadvantages of observational studies. They're usually just association. If you want to try to make a causal assumption, you have to make a causal kind of model. You have to make these very stringent assumptions that are usually non-testable. The measure of interest may not be available in some of the retrospective databases that exist. You're going to have confounding, and you're also going to be subject to kind of that missing data. So any questions on common types of biomedical studies? No.
Can you contrast a case control study versus like clinical trial? Because I know you can have like a case control within the clinical trial.
Yeah, at least my thinking of it is that case control studies are very focused on studying some rare outcome of interest, right? So I use, colorectal cancer because I studied one. I was on some projects looking at colorectal cancer back in the day. So that study was very focused on recruiting individuals that had colorectal cancer and then finding kind of matching controls and then just studying them, right? Studying whether or not there was different parts of their DNA that was associated with that risk of developing colorectal cancer. While clinical trials, however, are very interested in trying to study, okay, if, say, we gave a selection of individuals that maybe are pre-risk to colorectal cancer, and we change something about their diet, does it decrease the risk of developing colorectal cancer? So it kind of has that perspective looking forward nature. Does that help? Yeah. Yeah. Okay. All right, so next up, just talking about sampling techniques. So this will kind of determine how you potentially analyze the data. So three kind of common approaches. We have the simple random sample, whereas one where each person in the population maybe has the same probability of being selected into the sample. And this is pretty a common type. Stratified random sample, which is where the population is participated into different strata. And then with even each strata, a sample, simple random sample is taken. So maybe we, each strata being a different building, right, on Duke's campus, and we sample like 10 people from each building or something like that randomly. Cluster sample, the population is partitioned into clusters, and then we randomly sample a subset of the clusters and either measure all members of that cluster, or then within that cluster, we do another random sample within the chosen cluster. So potentially we randomly select different buildings right across Duke's campus, and then we either use everybody in those buildings or we kind of randomly sample within those buildings. Okay. Any questions so far before we move into some kind of simple exercises? All right. It doesn't look, all right, so exercises, there's three questions. So how many people are kind of following along at home or on their laptops? We'll just go over these together and then we'll take a little break so I can fix the Google Sheets problem and make sure that everybody's on the same page. Okay, so question one, the Jackson Heart Study is a prospective cohort study of 5,306 Black Americans, 21 to 94 years of age, at enrollment in the Tri-County area of Jackson, Mississippi. The primary outcome of the Jackson Heart Study is adjudicated cardiovascular events, so heart failure, stroke, myocardial infarction, and participants were followed up for about 8 years to determine if they experienced such an event. So baseline data was collected from 2000 to 2004, and we have demographic information, survey responses, and clinical measurements. So researchers at Duke used baseline survey responses from Jackson Heart Study to determine if there was an association between the amount of time since the participants' last routine physical and their perceived trust in healthcare providers. Those with missing data on measurements of interest were excluded. So what is the research question of this, this Duke study?
There was an association between physical demand and the trust in health providers, but the question is there a difference?
Yeah, so here it is just, is there an association, right? Like, are they correlated with each other or are they not correlated with each other potentially, right? So looking at, say, that time since the last physical, and then some measure of perceived trust of their medical provider. And I don't necessarily know how they measure perceived trust, right? I know there's surveys probably for that someone's developed. Okay. What is the primary outcome of the Duke study? Yep, time since last routine physical. Okay, and is the study prospective or retrospective? Retrospective, right? The baseline data were collected 2000 to 2000. All right. Okay. Question 2. We have a excerpt, the abstract from this publication. Just look at the effects of potassium supplements on glucose metabolism in African Americans with prediabetes, a pilot trial. So, low potassium has been identified as a risk factor for type 2 diabetes. Low potassium could be a potentially modifiable risk factor, particularly for African Americans. Objective, we sought to determine the effects of potassium chloride supplements at a commonly prescribed dose on measures of glucose metabolism. Design, among African American adults with prediabetes, we conducted a double-blinded pilot randomized controlled trial that compared the effects of a dose of 40, I'm not going to read that, as KCI supplements with a matching placebo on a 2-hour change in glucose AUC measured from oral glucose tolerance tests. The principal investigator performed chart reviews of the electrical medical records of patients from participating Duke primary care clinics who had been seen in clinics in the previous 12 months. To be eligible for the studies, participants had to be African American by self-reported race, aged over 30, and have prediabetes. Enrolled participants underwent a 3-hour 75-gram oral glucose tolerance test. After completion of the test, participants were randomly assigned to receive either the treatment or placebo. So, is this a prospective or retrospective study? Yep, it's a randomized clinical trial, right? So yeah, prospective. How would you describe the population from which the sample was drawn?
African Americans aged over 30 with
prediabetes. Yeah. Also at Duke primary care clinics. Yeah. And then what is the primary outcome of the study? Okay. Right, where's that glucose metabolism change for that 2-hour period? Okay. Any questions on question 2?
I have a question 1.
Yeah.
Area.
There's
kind of 2 factors you're correlating.
Yeah. So I guess here it's kind of more of a study of kind of this general correlation and association between these 2 variables. So I guess here the thinking is likely that trust is the variable that is impacting time since last treatment, which is maybe why they're kind of framing that as more of the primary outcome, potentially. You have less, yeah. Let's, I'll search for this. Maybe I can find the article. I wonder if Tina was on this. But that's kind of my perceived kind of why we're looking at that. Okay. Any other? No, doesn't look like anything in the chat. All right, question 3. A lot of text. So nothing is known about peripheral levels of serotonin in SIDS infants, so sudden infant death syndrome. So in the Curtin study, we addressed this issue by analyzing serum 5-HT, the serotonin levels, a peripheral marker of that metabolism in SIDS cases compared with autopsy controls. This information may provide insight into the extent of defective serotonin pathology in SIDS. So whether it is a generalized disorder of serotonin metabolism, and if measures of serum serotonin could ultimately be used as a biomarker of peripheral and central abnormalities in autopsy infants, as well as living infants at risk for sudden death due to, say, central serotonin defects. We specifically hypothesized that serum 5-HT levels are altered in SIDS cases compared with infants dying of unknown causes. A cohort of SIDS cases, 61, and autopsy-controlled infants, 15, were accrued from 2007 to 2013 in collaboration with the San Diego Office of the Medical Examiner in San Diego County. Serum was available for research under the auspices of California Law, Chapter 955, Statute of 1989. I didn't have to read that. The case and control adjudications were based upon autopsy reports, clinical information, death scene investigations, and were performed blinded to serum serotonin values. In this study, all SIDS cases, classified according to the National Institute of Child Health and Human Development classification of SIDS, were sudden, unexpected deaths of infants under 1 year of age that remained unexplained after a complete autopsy and death scene investigation. The controls consisted of seemingly healthy infants who died of definable acute disorders with no or only minor signs of clinical illness within 1 week of death. So, what type of sampling technique was used for this study? Outcome-based, exposure-based, both neither prospective or retrospective.
Okay.
Yeah. So, yeah, it's based on that kind of SIDS or not. And it's a retrospective since this data already exists and was collected from 2007 to 2013. How would you describe the population which the study sample of 76 infants was drawn? Yeah. So it's infants less than 1 year who died between 2007 and 2013 in San Diego County, California. And then the primary outcome of the study is basically looking at that SIDS, right? Whether or not it was a sudden infant death syndrome. Okay, make a note. So, any questions so far before we go for break?
Primary outcome, serotonin level?
Well, so they're sampling based on the case control status, but then they're likely going to perform some sort of logistic regression with that as the outcome and seeing whether or not it's associated with the serotonin levels. Yeah. Typically, yeah, these kind of case controls.
The other one, was the primary outcome was the dependent variable, was it, yeah, like the readout.
I think, it's likely due to wanting to kind of measure the serotonin as kind of a precursor to kind of predict the potential SIDS, which is why it's a potential outcome. Likely, the kind of question I think that you're getting at, which is maybe say looking at whether mean serotonin levels differ by SIDS status, is potentially interesting, right? And something that could be done, but they're likely more interested. Okay, like, what's that association with, say, the risk of, the odds of that, the odds of SIDS. Yeah. That's why case control studies, you can really only study the odds of an event, not the risk of an event. Okay, so there's no,
Can I follow up?
yeah.
When they open up the, I think nothing is known about her level of
Mm-hmm.
So that was kind of ending up what their main objective is.
Right.
And they say in the current study, I guess it's analyzing film
Mm-hmm.
in this case. I'm still like kind of confused how is the outcome, the primary outcome. Because I would assume you already know.
Yeah.
You have your cases.
Yeah. Likely it is just that in most of these case control, you're sampling on the outcome of interest. So you have, this exposure / potentially modifiable variable that you're interested in studying, or exposure, but the main outcome is something that's already occurred that you're trying to sample on. And so, likely they're doing that with the hope of potentially studying whether or not serotonin is associated with the odds of SIDS. And if it's not, but it regardless of whether or not they analyzed it either way, it's likely you saw an association one way, you see an association the other way. But it's just a matter of what is the actual question of interest, and if it's basically in the potential future analyses. If it's using this as potential predictive or something like that, you maybe want to have SIDS as the outcome. And a lot of case control studies, you kind of are sampling on this outcome of interest.
Mark, the variable kind of act, like literally what in the real world is the effect of the cost?
Of a potential cost.
Right.
Yeah. Yeah.
So once you have your primary outcome, if there is the potential, once you have the data for, and you think based on literature there's more options, you could tack on an exploratory aim or something like that to kind of see some of these other things that you may be wondering about.
Yeah, there's usually like secondary analyses that could be done, especially in a rare samples like this, right, where you want to make sure you're using as much of the data as possible.
Looking at more combos, looking at more effects, serotonin, not looking at more frequency.
Well, it could be also, say, like they run, they have these, say, vialed samples in a freezer somewhere, right? They look at serotonin, but then maybe they look at other, say, metabolites or something like that to see if there's an association with it down the line. If that makes sense.
I think that was good. Other things.
Yeah. Right. Right. And it's likely that's a great way of putting it. It's like, does SIDS increase your mean serotonin levels? Likely not.
Would not be other things being the other causes, because an outcome in this context means cause of the phenomenon. Right.
It could be maybe other potential exposures, if that makes sense, or modify it, or something along those lines. Something that occurs that's associated with the odds of SIDS. Yeah. It's tricky. All right. So now we're going to be moving into more kind of stuff on basically data types and what have you. So if you want, prior to, what's getting up, you kind of want to scroll up here to these sections on case study 1 and run this code. You want to run the libraries above this. So I'll kind of restart this. I'll restart my R. Julia, did you get the GitHub repository when it was up there on Zoom? Okay. All right. So we're going to run the libraries. We'll just ignore this for now. And then we're going to run this data. So this is going to load the case 1 data, which we'll be using. And then we're gonna read in the case 2 data. Okay. So, all right. So let's move into data types and summary statistics. Would people prefer me reading off of the R script or the HTML document, or going through the teaching off of the R Markdown or teaching off of the HTML?
Maybe the R script.
Let's do the R script. Okay. So we're going to be talking about some common data practices. So once the kind of the data are collected, we want to examine it. So we're going to be talking about some summary statistics and kind of graphical displays. And prior to looking at the data, it is always incredibly important to know or talk to whoever collected the data and get an idea of what missingness means or whatnot. So, what does a missing response mean in your data set? Is it 999? Is it negative 999? Or is it NA? Or is it some other marker? Is it missing? Is it missing lowercase? You have to kind of take into these accounts. Is it just missing? It's missing the G. You have to kind of worry about these kind of things. I definitely one time was analyzing some data and I was like, well, we have a lot of category 9. And they were like, that's missing. I was like, great. We next up have, you want to look at the continuous data. Are there measures that potentially aren't meaningful or seem like they're potentially incorrectly coded, right? Is it, say, if you're looking at somebody's body weight longitudinally and all of a sudden there's a drop of, 40 pounds that they then put back on the next week? Is that an actual correct entry or did someone put in the data incorrectly? So you have to kind of look at this and take that into account and reach out to whoever you're kind of working with or double check the data yourself if you're the one who's kind of entered it. But sometimes these unusual measurements are informative, so just you want to make sure you understand what's potentially going on. All right. We're going to be talking about 2 different terms here. The numeric kind of, we're talking about central location, which is typically like the mean and median of the data. And then we're going to talk about the spread, which is measuring kind of how variable the data is. And we're going to be talking about which one of those different approaches is most applicable for different data types. And then for graphical presentations, we'll be talking about, say, how to analyze categorical data, how to visualize categorical data if possible, how to summarize it, how to summarize quantitative data, and via basically ggplot or some base R functions. Okay. So first off, categorical data. These are data that are grouped into classes. There are typically kind of 3 categorical data types. There's the binary, where there's, let's say, only 2 values are possible, and they cover all possibilities. So dead, alive, right, would be an example. Virological failure, so say whether or not they're virally controlling or not. Sex, that's not really anymore. HCV test results, say reactive, non-reactive. And so these are all kind of some examples of potential binary variables out there. So nominal values are basically more than 2, right? So they're unordered groups. There's no natural order. So it could be randomization arm. Say you have 3 different treatments like placebo, treatment 1, treatment 2 with a new adjuvant, or treatment 2, which is treatment 1 with a new adjuvant. There's no real ordering there, right? Race is an example. HIV drug class, what are they taking? Those are all kind of examples of nominal data where there's no sorting that's meaningful. And then ordinal, which are basically values that are that do have a natural ordering. So a common example is Likert scales, which are basically, are you not at all sure, somewhat sure, very sure, extremely sure? If you break down a continuous variable into various categories, so HIV RNA, you look at, say, they have less than 10,000 copies, 10,000 to 100,000 or 100,000 and more, you're kind of breaking it into an ordinal categorical variable. And again, as I kind of mentioned, you want to be careful when looking at this, because if measured potentially as a continuous data, you may run into instances where I think SAS does this a lot, where there's negative 999 will record it as like an NA or something along those lines. So this is something you kind of want to keep an eye on. Any questions on categorical data so far? No? Okay. All right, quantitative data. So these are, they're on a scale or a continuum. So there's two types. There's discrete, where the possible values are countable. So hospital readmissions is a discrete variable, say like after initial discharge, it's 0, 1, 2, it's very set. On a scale from 0 to 10, how satisfied are you with your current HIV doctor would be an example of a potential discrete continuous variable, quantitative variable. And then continuous is basically where a value can potentially always exist between any of the two given numbers. So there's an uncountable set of potential values. So age, BMI, viral load, CD4 count, blood pressure, and so on and so on and so on, right? There are like infinitely many values that can be taken between like a viral load of 100 and 101, right, potentially. So there'll always be measurement limitations, right, in terms of the accuracy, but conceptually there's always numbers between those two numbers. And in addition, you can have kind of interval or ratio data, so data that's on some little interval, or a kind of ratio of two existing values. So let's look at our case one and see what kind of data we have in here. So, oh, that's not good. Oh, let's see. Sorry. There we go. Okay. So if we run summary on case one, that's the data frame that I read in from that HVTN 505 study. It gives us information on each of the different variables in the class. So we have treatment, and it's telling us it's a character. We have publication ID. We have treatment again. We have this MIT indicator. And then we have a bunch of different numerical values per protocol, DNA 1, DNA 2, DNA 3, these different indicator variables, which we'll potentially talk about later. Age, gender, race, BMI categorical, this behavioral risk score, and so on, right? So there's a lot of different potential data types in there. And then if we look at case two, we have such as SID, that's an ID variable, non-adherence. So case two was looking at non-adherence. We have gender, we have age, we have time value, and we subsetted this to just the baseline. We have CD4 count, viral load, weight, type of medication, the viral load bound, like is the data recorded at a lower or upper bound, right? Because like, well, hypothetically, you could have, 20 trillion viruses or something. The machine can't measure that many. Actually, you may not be able to hypothetically have that many. Death, log 10 viral load, and so on. Okay. So once we have that kind of data, we want to try to come up with some summaries of that data. So we're going to be focusing on five different things. We're going to be focusing on the mean, the median, as measures of central tendency, and then we'll be talking about for spread, the variance, the standard deviation, and the IQR, the quartile range. So we're going to first off, though, introduce some kind of notation for data values. So this is just kind of to get you all kind of in the little stats, math lingo. So for our cases, the sample size, we're going to be denoted as N. So for case 1, it's 2,504. For case 2, it's 320. And we're going to denote them as basically say like Y1 corresponds to the first observation, Y2 corresponds to the second observation, so on, and Yn corresponds to the last observation, okay? So let's say we sampled 5 individuals with HIV and measured their CD4, our N equals 5, and say these are the kind of 5 measures we have. We have 194, 87, 385, 241, and so on. Okay. And then if we wanted to run this, what it would look like, we're just going to make this vector that has this data because we're going to be playing with it later on. Okay. So case 1, N is 2,504. And if we looked at Y1 in our data set, let's say like age, it would be, we could get at that basically by just saying head. So head is the first 5 of a vector. And I'll say, okay, 35, 42, and tail will display the last 5 of the vector. So we can see the last one is 18. Okay. Now let's say that that data was entered based on geographical location, right, of the centers that they were studying, right, from, let's say, from West Coast to East Coast. If they entered them East Coast to West Coast, would you expect the same Y1 and Y2 and whatnot? No, right? Because so this is, it's useful with regards to the data frame you're studying, but it's kind of always going to be into how we read that data in, how we're processing it. Which is why there's the publication ID, which links to that person. Okay. So likewise, if we wanted to look at the log 10 HIV viral load in case 2, we would do head and tail, and we would get that the first one's missing, second one's 1.39, and the last is 4.49. Okay. So next up is the order statistics. So that data as is, right, is in no order. But let's say we wanted them to be ordered from smallest to largest. What the typical notation for this is you basically put it in parentheses. So now Y parentheses 1 denotes the smallest observation, and Y parentheses N denotes the largest observation. So Y1 is less than Y2, and so on and so on and so on. So for the CD4 statistics, it's written out there, but if you do sort CD4, you'll get that, 37, 87, 194, 241, 385. And you compare that to say how it was entered. So you can see it's kind of sorted. So Y3 is actually the smallest. No, sorry. Y5 is actually the smallest one. Okay. And we can do something similar for case 1. So this is a little bit tricky. There's a lot more data. So the way, at least I do it, arrange by age. Let's drop the missing age observations. And this arranged option is basically sorting the data from smallest to largest. And then I'm going to drop the missing age values, and then I'm going to slice. So that's going to grab the first, the second, the third, and the last age observation. And this is after we've already sorted it. All right. So we get that it's 18, 18, 50. And this could also be gotten via using head and the sort command. That's 18, 18, 18. Or if you, tail. Okay. Likewise, we can do the same thing for log viral load for case 2. And we get 1.397, 1.397, 1.397, then 5.69. So likely 1.397 is some lower bound, right? That's always something with like looking at this kind of these assay-like data. When you see some value that's that cures a lot, that has that kind of level of specificity, and it's a lower value, it's usually a lower bound of some sort. Okay. So that's just general descriptives of typically how we kind of write numbers and whatnot. So measures of central location. So first off is the arithmetic mean. So this is just defined as the average of all n observations in the sample, denoted as y bar typically, and it's defined as just the sum divided by n, right? So you just sum up y1 through yn and you divide by n. So for the CD4 sample, you do some arithmetic, like we're back in school, and you'd get that, and then or you can just use the mean function in R, and it'll give it to you. Or sum of CD4 divided by length of CD4. So 188. Okay. All right. Now let's look at case one. Let's get the mean age of these individuals. So if we just do mean case one age, all right, there's no missing data in this. So it's 31.395. So if there's missing data, it'll give you back an NA. So you have to add this NA dot remove equals true. So if we wanted to now look at case two and look at the log viral load, what am I doing? It's NA, right? Because there's some missing data within that. So R in general doesn't know how to deal with that. And so if you take the mean, it's 4.751, basically. And so what it's doing is basically it's taking out those values, if I recollect correctly, that are NA when it's for the denominator. So we do sum of case two EL log low NA dot remove true, and we divide by sum of is not NA case two EL log 10 load. That should give us the same value. So it's taking out those values that are missing in the denominator when it's calculating the mean. Okay. So typically when we have, say, a binary variable, we kind of measure it, or any kind of variable that's broken into kind of nominal levels, we can break it up into kind of the proportion that meet that criteria. So what is the proportion of individuals that identify as that specific gender? So if we just wanted that, and we just wanted to sum up how many people identify as male or trans female or female or non-binary, we could do this in R. So if we do case one, count gender, it'll give us kind of a count. I'm going to pop this open in another window. It'll give us the count of what the people that I potentially identify as in this study. So we have 8 individuals who identify as female, 2,460 who identify as male, 6 as other, 28 who identify as transgender female, and 2 that identify as transgender male. And if you wanted the proportion, you would then have to say divide that by the sum of that n. So we could do this basically, mutate proportion equals n divided by sum of n. Oh, no. And that'll give us kind of the proportion that fall into each of those categories. Okay. All right. So, if say we wanted to get a little bit more deeper and we wanted to know, all right, well, what is the proportion in the treatment arm versus the placebo arm of each of those? We basically just go count. We do case one, we do count, gender, treatment. So this right here will just basically give us a breakdown so you can see, all right, there's 4 individuals, placebo in the female, there's 2 placebo the other, 15 trans women, 1 in the trans male, and so on. And then if we want the proportions, what we do is we group by gender, and then we take that in and we divide by the sum of that in. So this is looking at the proportion that were assigned with, to say, placebo within that gender. So the n is going to be respected to the total n of that identified subgender. So let me run this over here. Oop. Oh, I forgot the treatment part here. Sorry. So we can say, all right, 50%, 50%, so on and so on and so on. Okay. Clearly there's like a rounding thing here going on with that. And so given what we know about this trial, is this kind of what do you all expect of this? Is this kind of what you think? What would you expect to see in each gender? What would you expect to see the treatment proportions be? Yeah, 50-50, right? It was randomly assigned. So, you know, there should be no differences within a gender by treatment, right? So this just gives it that, and then if you wanted to gussy it up a little bit, you could do the pivot and get kind of the proportion in the placebo, and then, you know, vaccine for each. Okay. Any questions kind of on the mean? So the mean of a binary variable is just its proportion. Any questions on that?
Yeah, there are categories of male.
Given I think they defined it as males and transgendered women who have, well, so I'm not familiar enough with that topic, so I imagine.
I think it
was, yeah. So I think it was, I don't know enough about the recruitment, but yeah.
They
didn't exclude anybody, yeah. So, okay. So next up, we're talking about the median, right? So median is also kind of goes hand in hand with everything. So this is the value at which half of the samples are below it, right, and half the samples above it. So if n is odd, it's the middle number, and if n is even, it's the mean of the two middle numbers. And it's typically denoted by m. And so in the CD4 example, we have only 5 numbers. We've sorted it here for you. What's the median? You're nodding, but I want you to hear it. 1, right? 94. Okay, and so if n was equal to 4, it would be the median of those 2 numbers. That's the value of which half are above and half are below. Okay. So if we want to look at the median age within case 1, right? It's just median, case 1, $age, and that'll tell us that the median age is 29. Another way you can do this sometimes with this kind of data is median, is put it in double brackets. So they give you the same results. Okay. And then case 2, let's look at the median of the log 10 viral load. What do people get when they run that? It says, yeah, 4.79. Yeah. Okay. 4.879. All right. So how do we then say choose a measure of the central location? So for categorical data where it does kind of have those proportions, you generally just kind of present counts, right? And like for just means and proportions, count and percent of people that fall into those categories. For continuous data, the mean or median, it depends on kind of the shape of the data and the distribution. So if the data is symmetric, they'll be approximately the same. And then people typically use the mean. So here we have some examples of some common distributions. So we're going to generate from a beta distribution. So let me show you all what a beta distribution looks like. I go to good old Wikipedia. So, it takes these different parameters as alphas and betas, but it can have very different terms, right? So it's not necessarily symmetric. So if you look at this kind of orange one here that I have my finger on that touched this board, it's not, it's not symmetric. Okay. So we're going to set a seed and we're going to generate some beta data. So this is basically just generating a bunch of quantiles, and then this D beta stands for distribution of beta, so it's going to generate some data from a beta distribution with alpha and beta of 0.5. So we're going to get this data frame with kind of the proportion and then the value. So 3.19 corresponds to a density of 0.1, and then we're gonna plot this. And then we're gonna basically compile all these together. Then we're gonna do this again, but we're gonna generate 300 random ones and kind of plot this with it. And then let me just run this. Okay. Cat plot. Okay. Come on, compile and look nice. All right. So we have a couple different distributions here, right? We have the beta on top. We have the probability density function. We have the normal, right, which people have all seen, right, the nice bell curve. We have the T distribution, student's T distribution, which is similar to the normal, though a little bit sharper slopes. And then we have some kind of histograms and whatnot of some randomly generated data. So these are all relatively symmetric. They are symmetric, right, in these cases. So the mean and median are going to give back the same results, right? Okay. So asymmetric distribution is when there's some skewness. And this is when there's some extreme values that are really influencing the mean. And so this could be in a case, right, where you maybe want to report the median value. So we're going to generate from a chi-squared distribution with 3 degrees of freedom. And then we're also going to generate a exponential. And then finally a beta with different parameters. And then we're going to use cow plot. I just like saying. Okay. Right. So these are ones where you see the data is very asymmetric, right? And where the mean and the median would not agree with each other in these cases. And so for these kind of instances where you have these kind of extreme values, you potentially want to report the median more so than the mean. Because if you have one extreme value, it can really influence the mean value. Okay. So, I mean, we can go over kind of, whether or not you have the mean or it's higher than the median, it kind of depends on the distribution, but we won't go over that for now. So, look at some more skewed data. Where basically we have the mode. So the mode is the most common value, the median, and the mean. So, you kind of always want to plot the data and get an idea of how close the mean and the median are to each other. And there may be instances where the data may look skewed, but the mean and median still maybe are close to each other. It's just a matter of being familiar with your data to try to decide kind of what is the best summary measure. I think the median is usually the safest, right? Because it's the most robust to potential outliers. Okay. All right. And yeah, again, the more highly skewed, the more reason to use that median. So any questions on central tendency so far? Chat, doesn't look like anything. Okay. So next up, we're going to talk about measures of spread. So this is basically looking at how far the data are going out. So one of the most common is the sample variance, right? Which is the average of the squared deviations of each value from the mean. So basically, you've calculated the mean value, and you basically subtract it from each of your observed values, you square it, and you take that kind of value, and then you divide by 1 over n minus 1. All right. And the 1 over n minus 1 is due to the fact that if you take 1 over n, instead, that's a slightly biased value measure of the variance. That goes away as n gets increasingly large, but it's a potentially biased value. So we do 1 over n minus 1. It's also for the loss of degrees of freedom because you've estimated the mean in the data. Okay. So the example CD4 sample, we know the mean is 188, and then we can calculate the variance in R as the variance of CD4, which we get this, very large value, 18,663. So if you wanted to calculate this, it's basically you take CD4, you minus the mean of CD4, square it, right? That's giving us that summation values, 27,000. You sum it, then you divide by 4. So that's kind of what is going on in the background. So it's probably using some computational tricks to make it faster. If we want to look at age, right? The variance of the age in case 1 is 81.3. And then within the case 2, the log 10 viral load is 0.68. Is the sample variance. The one thing I've seen that's always interesting is sometimes, do people ever calculate the coefficient of variation within, like, say if they're doing assay data? Does anyone here do assay data? Like, I'll see, like, within Excel, there's like a population standard deviation and a sample standard deviation. The population standard, they're using that 1/n versus 1/n minus 1. And it can give you very different values for the CD, depending on what you use. But I don't have a good philosophical reason for using one versus the other in that case. But anyway, yeah, so this is kind of this classical sample variance estimator. Okay. So these values are kind of larger, right, than the observed values because of the fact that, remember, they're on the square. So they're on the age squared value, basically. So the sample standard deviation is then the square root of that variance. So if you wanted to calculate it in R, the function is SD, CD4. So it goes down to 136.61, which is much more kind of within the range of the CD4 values, right? And this is literally just taking the square root of the variance, right? Is all it's doing. For age, in case 1, we get it as 9.0. And then for log 10 viral load, it comes out to 0.825. So this is kind of a common measure of spread that you'll see. Okay. Next up, we'll talk about the interquartile range. So general notation, 100 times P percentile of the data is the value at which that percent of the data is less than or equal to this value, and then 100 times minus P may be above that value, typically known as Q of P. So if we let P equal 0.1, the 10th percentile is the number in which 10% of the data is less than or equal to the value, and 90% of the data is above that value. So if we had these order statistics 12, 13, 15, 15, 16, 17, and so on, the 10th percentile would be any number in that interval from 12 to 13. So like 12.5 would be a 10th quartile, because 10% of the data is below it and 90% of the data is above it. And then the IQR is the distance between the 25th and the 75th percentile of the data. So it's where like 50% of the data kind of lives in the central part of the data set. So to calculate this for the CD4 data, right, with n equals 5, we have 37, 87, 194, 241, 385. So the 25th percentile is 87. The 75th percentile is 241. So the IQR is 154. It's the range of the data. And if you wanted to calculate that in R, if you wanted to find the quartiles, you do quartile, CD4, and then you give it the proportions you want. And then there's also an IQR function within R. And then I think if you wanted to, I believe all it's doing is if you do the quartile, diff, yeah. So it's, sorry, quantile, not quartile. And it's basically, it's just taking the difference across those two values, right? Okay. So within, let's look at age. So if we want to know the quantiles, we run quantile, case 1 age. We want the 25th and the 75th. It'll tell us it's 24 and 39. And then the IQR is in 15. Okay. For case 2, if same trick, not trick, but you get what I mean. We have 4.42 and 5.33. And then if we run the IQR, we get 0.9. Okay. And what you'll often see is table 1s is they'll report it as this kind of Q25, Q75, and then they'll typically put the median value out in front of the brackets, right? So he gets an idea of kind of the spread, or kind of either that or the min and the max values that are observed for the data. Okay. So these measurements are very sensitive to outliers, the variance and standard deviation, and skewed data. So it's basically kind of like, you can think of it when you're able to use the mean, you're likely able to use the variance and standard deviation, right? And it makes sense because it's a measure of the spread around the mean. And so it should be used when the mean is able to be, capture that kind of centrality of the data. The ICR, on the other hand, is robust the outliers, and so it can be used with, the median is used and when the data is potentially skewed. Any questions on that before we go into exercise? Okay. All right, so these are going to be some kind of general questions. How would you all like to do this? Would you all like to kind of work on them yourself, or would you all like to go through them together? Okay. Go through them together. All right, so let's read in the case 1 data. And so first off, we're going to ask this kind of question, which I didn't define what tidy means, but tidy is kind of this terminology or type of data frame where it's like very clean and organized. Each row is like a single observation. It's rectangular in shape, easy to kind of clean. It's very different from, say, reading in a file where, like day 1 observations are here, day 2 observations are here, day 3, day 4, or something like that. Okay. So we read in case 1, and then I'll let you all kind of look at it. And so, does it appear tidy? This is much easier on the HTML because I can hide the code. Yeah.
Our versions do have the code for the answers?
You should, yes. So this one is just kind of it should be in there if you're looking.
Oh, okay.
Yeah. So, but this question right here, do the data, so if we were here, it's like kind of hidden, the answers. So do the data appear tidy? Yeah, kind of relatively speaking. I've seen much worse. We kind of have each row is an observation, right? The column, we have publication ID, and I bet if we looked at length of unique, case 1, publication ID, it's 2000, so there's no repeats of publication IDs. That's always good to see. So it looks pretty tidy. So how many individuals are there? And how many variables are in the data? And how many individuals ended up with an HIV infection? So the way we can do this is we have case 1, and then we type to summarize, and we say unique, and we say, give me the number of distinct publication IDs. So that's what indistinct is doing. So it'll tell us, all right, there's 2,504 distinct IDs within this study. And let's assume that they're all unique people. I had a project once where it was like genomics, and they were giving, I think, some cash prize, cash money for people to participate. And somebody came in 3 or 4 times, but it's genomics, so we can tell. Like, it's not like there's like, like quadruplets came into this study. It's like, all right, this is just the same person. So if we want to know how many variables are in the data, say dim this in. So this is just basically giving us the number of rows, 2,504, and the number of columns, 27. Okay. And so if we are interested in the HIV status, so this would be something like if we looked at, so I think I loaded it, but we didn't really go over it. What was it? Data dictionary. Let me see. Okay. So if we look at this dictionary data set, there's a HIV. So we'll just use this where it's basically indicator of an HIV infection in a MITT cohort. So the MITT was a subset of the individuals that I believe were HIV negative at the time of enrollment, I believe. And it was a separate kind of sub-cohort within the study. But anyway, so let's look, so we can say, all right, we're gonna add margins to this table. So basically what this is doing is we do table, right? It'll compile after a little bit of thinking. How many, right, have the two, so there's 2,424 that did not have an infection and 80 that had an infection. And then the add margins just kind of adds a sum over them. So this is more useful when you have like a bigger, you know, when you say you have a 2x2 table. Okay. All right. Now let's take a simple random sample without replacement of size 100 from the data, set a seed so that it's we can replicate it, and how many of the individuals are per protocol. So per protocol is this variable PER, PROT, and it's kind of an indicator that they received all of the vaccine boosters, right? Because asking someone to come in for 5 of these is probably a big ask, and not everybody's going to show up for all of them. So I'm going to set a seed. I'm going to take a subset of them. I'm going to using this sample in and with size 100 with no replacement. I have 100 individuals now, and then I can look at how many are per protocol. So 69 of them are per protocol. Okay. When the outcome is rare, is it better to perform a cohort study or a case control study? I typically think case control, but I guess this maybe isn't a good example for this, since this was a clinical trial, but right, it's typically better for these kind of rare cases, rare outcomes. Okay. So next up, for the following variables, which of these do you think are actually meaningful? Like, is the mean and median potentially useful? So let's look at these. So I'm going to bring up case 1. All right. So is publication ID, is mean and median meaningful for this? No. Is race fool meaningful? So let's look at race fool. So race fool is this categorical where it's getting down into kind of what the self-identification is. Is it meaningful for this? No. Is treatment, is it meaningful? So if we go to treatment, here it's placebo vaccine. Yeah, so for the binary one, it depends, I guess. So because you could code it as a 0 and 1, but that's just the treat variable. Yeah, yeah. Okay, age. Yes. BMI. All right, let's look at this other race variable, which I think is just, they coded as white or not. So it looks like 0, 0, 1, 1. So here it could be meaningful. HIV. This is a yes, no, yeah. BMI category. So this is kind of broken down into ordinal. No, right? It's not necessary. There's lots of different values here. BHV risk. So this is we'll talk about some of these. They also have this pretty detailed behavioral risk score for these individuals about what risk practices they take into account, they participate in. So they basically have calculated this over a wide variety of risk scores. So here, you know, looks like it's continuous from kind of 0 to 1, so it may be meaningful for this variable.
Is that something that is standard, or is that something that was just done?
So I haven't fully read the method section on that but I'm assuming there's some literature behind their calculation of that, of the risk scores that they looked at. It's like a pretty, again, I'm not very much in this field. So it's a lot of, actually, let me just open up this data dictionary. Oh, this isn't gonna work. But, you know, it's a lot of stuff on like sexual partners, use of drugs, things along those lines. And so I will read up on the exact method of which how they calculated this. Whether not it's some kind of proportion that have categories, you know, that satisfy at least X amount of risk categories or whatnot. And we're using this one that they imputed because some people didn't put it down, so they did a single imputation of it. But yeah. Okay. DNA 1. So this is that indicator for, hey, did they receive the first booster, the first like shot in the 5 shots they have to take? Yeah, this should be meaningful, assuming everybody got it. So, and then let's look at treatment and gender. So treatment is just the treatment variable 0, 1. So I guess in this case, this one would be potentially meaningful. And then the gender, right? That's the one that has, I think, about 5 different levels, 5 or 6 different levels. It would not be meaningful, right? Okay. All right, any questions on that before we get into some graphical summaries? No? Okay. So, how many people have used bar plots before? Bar plots, yeah, okay. We're gonna go over bar plots, box plots, scatter plots, violin plots, and then matrix plots, yeah. So, all right, so a bar plot is just a common way to kind of graphically show some frequency data, you know, that's on different kind of nominal or ordinal categories. You have spaces between the bar, the height of the bar represents some count or percentage of the total, and the width of the bars are the same across different levels. Okay. So we're gonna first we'll look at just self-reported race within case 1. So I'm just taking publication ID and the race information. I'm dropping any NAs or levels. So now we just have this data set that just has basically the publication ID and the self-identified, self-reported race. Okay. All right, and if we wanted to do a bar plot, we take the data, we group by race full, we count. So, and then we do ggplot, AES reorder. This is basically reordering the data by N, so it'll look a little nicer. We specify some colors, the columns, and then we specify the text, and then we give it some labels. And then this is just, this part you don't necessarily need. This is flipping it. This is telling it the theme, and then this is telling it the scale of the Y. And I added this because some of the numbers were being cut off. So we run this. We get basically a breakdown of how the number of individuals in our study that self-identify or self-report as, you know, Native American, Alaskan Native, Hawaiian, Pacific Islander, report as other, Asian, multiracial, Hispanic, Black or African American, or white. Okay. if we wanted to do percentage, we would basically follow the same steps, only we would kind of add a point where we calculate the percentage, right? And then it's a matter of just kind of reorganizing. So this reorder statement right here is basically just to give it this kind of nice visual where it's kind of increasing as you move along, because otherwise I think it'll be sorted by, I think it would go Asian, just, Asian, Black, and then it'd be kind of, the bars would be kind of all over the place. Okay, so we count, we calculate the percentage, we take the, and then we reorder, and we do the geom call, which is the bar plot, and we add the text, and then we have the labels. So this should be percentage, and then get our plots. And so now, instead of the count, we have the percentage of individuals that self-reported under each of those races, those categories. So, and I think, okay, no, that is just 8%. Okay. All right. And so this will give you a kind of a sense of how many, like what are the most common categories or whatnot. Picture's worth 1,000 words, so, sometimes this may be useful. All right, we're not necessarily looking at transmission status. So for quantitative data, we may want to look at histograms, which are kind of a continuous analog of a bar plot. And this graphically represents some continuous data that has been split into categories. This is, again, you're kind of looking at the overall pattern, so shape, center, spread, and you kind of want the width of the bars to be the same for ease of visual interpretation. So let's look at case 2, and we're going to look at log 10 viral load. There was 3 missing, so we're going to just drop those. So we take case 2, this is the baseline. We say ggplot, AES, log 10 viral load, geom histogram, and then we pass some labels. And then what this is going to give us is a kind of frequency count of how many observations do we observe at each of these different values. You can see like around 5, there's about 37 or so individuals who have an observation of a log 10 viral load around there, and so on. So this is kind of not necessarily symmetric data. Okay. You can also break this down by, if you want to have it kind of separated by, say, gender or some other categorical variable. So we could look at, say, case 2BL. I'm just doing this so it doesn't show up as 0 and 1. Go ggplot, same stuff, but we add this facet wrap here. And so this is going to make 2 separate histograms, one within the males and one within the females. And so we can see kind of the breakdown of the different counts within the different. So in general, it looks like there's a lot more females in this study than males. Any questions on histograms or bar plots? This was case study 2, yeah. And then this was case study 1. Someone?
We're just interested in their population. South Africa, the race distribution.
Oh, no, case 1 is not South. Case 1 is the United States.
Oh, okay.
Yeah.
So yeah.
Case 2 is South Africa. Yeah.
I just want to make sure, because we were kind of looking at trends in race.
Oh, yeah, no, I switched it out there. So.
Yeah, it's okay, yeah.
Okay.
So we'll keep on track of which cases, which.
Yeah,
To make sure that some of this, like, doesn't show
I get you. Okay, so box plots, these are kind of pretty frequently used for quantitative data. I feel like I maybe use them more than histograms. And they provide basically a graphical display of the data. Like show the median, the 25th and 75th percentiles, and then values that are considered outliers. So these are values that are 1.5 times the IQR outside of the 25th and 75th percentile. If you want to do this, basically, there's some base R, and it's just basically a box plot function. And we'll show how to do it in ggplot a little bit. So box plot, case 2 BL, log 10 viral load, and then all of this information is just controlling the size of the text. And we'll get a nice little box plot of log 10 viral load in case 2 over the data. And then likewise, if you wanted to do it by some categorical variable, you just add a little tilde and you say data equals case 2 BL, and now it'll kind of have it by gender. And if you wanted to do it via ggplot, you know, very similar, we do the box G at the end, we give mutate, give the female male, ggplot mapping, say X is equal to gender label, Y is equal to log 10 viral load, we do G on box plot, we give it some nice labels. I tried to mess with the text size a little bit, and you know, we'll get the kind of the box plot and ggplot, that comforting gray background that immediately tells you that someone did it in ggplot. So these are kind of you know, some examples of some box plots, but is there any patterns, I guess, you all can see in these plots based on HIV within case 2?
It seems like male.
A little higher, yeah. Looks like it's a little higher. Okay, so this is useful, but you can always find instances where this wouldn't necessarily, the box plot would hide something. So this is why it's useful to also maybe have a histogram as well. So as an example, we're going to generate this data set that is going to be 2,000 observations. 1,000 is going to be from a mean 0, base normal, and 1,000 is going to be from a mean 4.5. Okay, let's look at this. So if we look at the box plot, it looks very nice, right? But then when you actually look at the histogram of the data, you can see that bimodal distribution that's coming from the fact that your data is coming from two different populations, not two different populations. So for this kind of bimodal data, right, the box plot's not going to be very good at picking that up. So you're going to want to have a histogram, or look at a violin plot. So this basically has the box plot in the center and then displays the density curve kind of the probability density function around the data. So for this example we just generated, we're going to make a tibble. This part is just because I couldn't figure out how to get this to work otherwise. And then we're going to do geom, it's just geom underscore violin. And then box plot on top of that if you want to see what it looks like. So this is kind of giving us the violin plot of that data. So you can see the bimodal nature of the data now, right? And then you added the box plot in the middle, which kind of shows the, you know, where you can't really tell. Okay. All right, and then next, finally, is, well, not finally, we're getting there, is, say, a scatter plot for quantitative data. So this is when you want to show the relationship between two quantitative variables, right, that are, say, paired in some way. So the x-axis gives some value, and then the y-axis gives another value for that same observation. So these may be, say, a predictor and a response, or something along those lines. And this can be useful for identifying clusters or directions of relationships and what have you. All right, so case 1, we're going to examine the relationship between age and, say, BMI. there wasn't actually any clear trends in these. There wasn't a lot of continuous data in case one. So I don't really, I mean, it's maybe the BMI's increase. I can't really see much of anything. I don't know if you all, yeah, I can't really. Yeah, no real trend. All right. And next up, in case 2, let's examine the relationship between weight and HIV RNA. We'll look at that log 10 viral load. So case 2, yeah, we got ggplot, weight, log 10 viral load, the genome point, and we do the labels. And you can see, you know, maybe there's a little bit of a trait where the higher weight, maybe there's a lower viral load, possibly, but nothing really jumping out. So if you tried to put a genome box plot in there, curious to see what would happen, actually. R will try to make one for each of the individual values that are observed for weight. So I think it'll just crash it. Yeah, that just crashes it. Yeah, it's like, they can't do this. Okay, cool, good to know. Yeah, okay. All right, sorry, that was my own curiosity. Okay. And then you can also say color code it if you wanted to by the gender label. So AES, I typically like to kind of put what each, so it'll automatically go X, Y, but I like to specify it so X equals, Y equals. So you have GM font, and so it's just going to automatically color by the gender. And then if you want, you can kind of add, if for exploratory purposes, and you can add kind of a smooth, if you wanted to say, get a linear relationship in there, separated by the 2 different groups. So what this will do is now kind of add this line of best fit, this linear regression line of weight on log 10 HIV viral load separated by me. Okay. All right, then finally a matrix plot, and this is just basically a series of scatter plots showing some bivariate relationship amongst, say, 3 or more variables. There's a lot of different packages to do this. We're using the pairs package, the pairs function in here. And we're going to look at case 2, and we're going to log 10 viral load, age, weight, and CD4. And what this is doing is it's fitting the lowest regression line over it. But what this will give you is basically you'll have for each of the variables, right? So this is log 10 viral load against age, log 10 viral load against weight, log 10 viral load against CD4, and so on and so on. So this may be a useful way if you have a lot of continuous variables of kind of looking at them all at once. And it's basically just a bunch of scatter plots, right? Kind of stacked on top of each other. With the X and Y axis, depending on what's on that row and what's on that column.
Can you talk about the line of code that leads to the whole panels?
Yeah, the lowest regression?
No, the whole panel, like how you have those things.
Okay. Yeah, so it's just this pairs. Yeah, so it's it'll just kind of automatically do this. So let me see if I get rid of this panels. Was there 2? Let's put case 1. Let's look. Was it BMI? Was it age? And then we'll put this BHV risk. Let's see if this works. Okay. So yeah, it's basically you're passing in some kind of formula, BMI plus age plus pH. You're telling it the data set to look for that. And then this is just telling it point size and what do you want the title to be. So this right here is case one, right, where you have BMI, age, and the behavioral risk score. Right. So it looks like the behavioral risk score is pretty categorical, to be honest, right? It's probably ordinal. So yeah, that's kind of the general way you do it. Okay.
You said came in which package?
I believe it's a base package, to be honest. It's not tidy. It's just a base package. Yeah. There's likely a tidyverse version of it, but yeah. Yeah.
And it's like, oh, okay.
Yeah. So you don't even have to load in a library. So yeah. All right. So any questions before we do some exercises? No? Okay. All right, so first off, we're gonna look at case study 2 and look for any outliers or weird values. And we're gonna try to determine which would be appropriate visualizations for these variables. So for now, we're just gonna look at the continuous variables. And we're gonna make this kind of grid plot that's gonna have all these variables. So this is using base R. So what this is doing is, the way that this works is you set some variable. So this right here, this is the key. PAR MF row equals C33. So what that's telling it is that basically the next plots, you're gonna plot on a 3x3 grid. And the idea is to get a general what the data looks like.
And how is that different from the pair?
So if you look at it, we're going to look at the histogram. We're going to plot the density, and we're going to plot the box plot. So we're looking at three different types of plots of the data, which is how it's a little different from pairs. Okay. So this can be like a nice way to consolidate data, and then maybe you output it to a PDF or to the data itself. So the way we've done it here is we've taken these 4-5 variables that we're interested in, and then we're looping over them. And we have a note here where it's like, okay, if it's 1 or 4, we're going to start a new. I think that's right. Am I remembering my remainders correctly? Yeah. Okay. We're going to start a new grid. Okay. So let me show you all what this looks like. Nope. Okay, let me see. II equals 1. So we're going to have this kind of base thing going on. We're going to do the first ones. All right. Well, we've got to run it all at once. All right. So, all right. So it's shown the first 2. So I'm going to 1 through 3, and then 4. Should do it. Nope. All right. It's getting rid of those. Sorry, y'all. Get this working. Figure margin's too large. Okay, I'll just do this. Okay, so we get the first plot, right? So we have here we have age, we have weight, and then we have viral load. Right. So this is, you know, the histogram. This is estimated density of the data. So, you know, 30% of the data is around 50. You know, 0.03% of the data is around 50. And then, you know, a box. So for viral load, at least to me, it looks like there's a few instances of people that have very high values, right, we may want to look into. And for weight, you know, potentially there's some individuals that are very underweight. And then for age, it's kind of looking rather symmetric, to be honest. Okay. Is there anything that strikes you all looking at it? Yeah, like a little bit with this second group of really high viral load over here. Okay.
Makes me want to peek in to see if the people with the high viral load are experiencing major weight loss.
Right, yeah.
Well, just raise the question, just be like, hey, I wonder if that's right.
Right. Maybe those are the people that are here in the lower weight, potentially, yeah.
Well, and especially probably giving treatments or anything like that.
Right.
So, yeah.
Yeah. Okay. Then, and then if we looked at the next two, which are basically log viral load and CD4 count, we can see log viral load is kind of skewed, and then same for CD4 is rather skewed. But, you know, maybe a couple potential outliers, you know, you may want to look at the CD4. You notice kind of on when you're kind of log transforming a data, it's still sometimes useful to look at the non-log transform data to give you a case of those outlier values. Because, you know, the value is going to be, once you take the log 10, right, it's not going to look as much of a difference. But yeah, so that's the general kind of consensus looking at this data.
For me, I only got, how'd you get the weight?
The first three? Yeah, I ran just one, so I split it up. So I ran 1 through 3. And yeah, through 1, and then I ran it again through 4 through the number of columns. But I couldn't run them all in one chunk. It seemed to override the existing one. Yeah. So I think you'd have to kind of break it up in some way. Okay. All right, next up. In case study 1, let's create a bar plot showing the percentage within each BMI category that received the vaccine. We'll drop those missing BMI for now. All right, just before we even start, what are we expecting probably as a proportion in each BMI category that's going to have the vaccine? What should it probably be around? Case study 1's the clinical trial.
Only 80 people with it, right?
Or the vaccine. Oh. Yeah, we're looking at the BMI categories by vaccine, yeah. So it should be about 50%, right? Okay, so we're gonna take that case 1 data, we're gonna drop the missing BMI, and then we're going to group by BMI category and count the BMI category in treatment. So actually, these lines should be reversed. That's it. Okay. So this first step is just going to give us a general breakdown. So we have each of the BMI categories, and then we have the count of how many received placebo, vaccine, and so on. Okay. And then I'm going to group by that BMI category, and then I'm going to take this N value and divide by the sum of N within that category. So that's what that group by statement's doing, right? So we now have that percentage. So let me double check this. It's 16 divided by 38, 42.1. Yeah, okay. So that gives us the percentage within the underweight, the under 18.5 BMI that are placebo. Okay. And then, you know, we just want the sum that are, sorry, the proportion that got the vaccine within each of these groups. So I'm going to filter just where the treatment's equal to vaccine. We can figure out what the placebo is from that, right? So that just gives us the breakdown. And we can see it's kind of within 50%, right? And then we follow the same text where we say, all right, ggplot, we're going to reorder that BMI category by percent. So this is now, this actually, I'm looking at this, and does it make sense to, for this bar plot where the X variable BMI category has an actual ordering to it, right? Does it make sense to order it by the percentage of vaccine, or should you order it by the actual value of BMI? Should be by weight, right? So let's run it like this and see what it looks like. Okay, off. Let's try this again. Okay. Right, so it's not in an order that necessarily makes sense, right? Because you have, all right, so 46.8% of the above 40 BMI receive the vaccine. So it's shaped by that, which doesn't necessarily make sense given the data we're looking at. So if we wanted to have it by BMI instead, it should be, barring a catastrophe, a simple fix where we replace this percentage with BMI, right? Because BMI is within there, it's kind of a, ooh, nope, it's not going to. So what we're going to want to do is we're going to add a new, we're going to change this a little bit. We're going to do group by BMI category. We're going to go summarize N equals N. And then we're going to go mean BMI equals mean of BMI. Okay. So what this is going to do is, if I did this right, it's now going to give us this kind of mean BMI variable out here at the end, which we're going to use to kind of sort by, right? Because it's going to correspond, it's going to roughly correspond to the BMI category, right? So that should be increasing with the BMI category. So, and there's probably a smarter way to do this. So now we see, all right, so the less than 18.5 or 17.7. So we just kind of taken this kind of, made this variable that roughly corresponds to the sorting that we want. Now, if we put that in there, see, and did it work? Yeah. So now we have it kind of ordered by, we have the less than 18.5 at the top, 18.5 to 24.9, 25, 30, 35, greater than 50, which is kind of the ordering that maybe makes a little bit more sense. Okay. Any questions so far? We're at the end of today's talk. So that's it. Any questions? Zoom, in-person people?
You guys just go over again the lowercase n in Tidyverse.
Do you mean this part right here?
First, yeah, whatever that box says.
Yeah.
That's the everything in a certain
Group.
being called on?
Yeah, so that in parentheses, it can only be used within dplyr, but it's basically just counting the number of rows that are within that grouping. So it's just saying, all right, how many observations are there that satisfy the unique pairings of BMI category and treatment that we observe? So
I thought it's the size of the number of rows. Did you call it the actual rows?
it's just the number of rows. So it's saying, all right, I mean, so in this case, it corresponds to observations, right? Because we know that beforehand. But it's saying, okay, there are 16 observations that are less than, have the BMI less than 18.5 and treatment equal to placebo. So it's kind of just a way of counting, basically. So if, say, there was multiple observations per person, right, this would correspond to something slightly different. You'd maybe have to filter a little bit to just individual unique row observations. But that N is just kind of a number. It's giving you the number of rows that satisfy that. Does that help? Yeah. So yeah, so you can set it to N. There's also a counts function, right, which is just counting the number that show up in each of these categories. So yeah, that's all it's doing. So if you didn't have summarize, let's say you just had mutate, I'm just gonna do select. Let's say you just had this, right? Sorry, you always forget one thing and then it messes up. Okay. You can see it's like just added for each row in N, basically, like how many rows, how many people, other people, in addition to 505,0001, there are 585 other people that are in that BMI category that received that placebo treatment. So it's just counting how many rows that satisfy that. I don't know if that's helpful at all. Yeah. Any other? Yeah.
I wanted to ask a question when you were talking about blinding.
Yeah.
How does it factor into like the analysis, like the different tiers of blinding?
Yeah, so I think in general, unless it's triple, so I'll be completely honest, I haven't worked on clinical trials of that nature, so I don't have a great answer for what exactly happens in terms of let's say like the triple blinding scenario. I know that there's typically a case where maybe you're unblinded or something, or you're not blinded to the data and you're just measuring, say, adverse events or something along those lines, which may lead to the data being unblinded if you're observing a lot of adverse events. But typically the statistical analysis, I think it's until the end. But yeah, I don't have a great answer for that. I apologize. So yeah, I'll get back to you. Yeah.
In my experience with clinical trials, I haven't done it.
Yeah.
But we
Yeah.
really need to know.
Yeah.
Because if it's already done in clinic.
Is it mostly, I'm wondering if it is mostly the integrity of the data?
For the triple blind kind of situation?
Yeah.
I'll have to read up more about the triple blind. I know the other ones are, likely for placebo effect, trying to get around that or any blinding, but the triple blinding, yeah, I'm not certain. So, I mean, maybe you can still bias yourself, right, if you're really hopeful. So, any other questions? No?